So these are the solutions to the questions on satellites for Newton's law of gravitation. Question one, the value of g part A, that should be straightforward. That's very similar to what we saw earlier on. So we've got our formula, we need to write that out. We know g, we know the mass. We should be given that. You're not expected to know that. The common mistake here is that students either just use the radius or they just use the height and they don't add the two together. And if they do, they forget to change kilometers into meters. So there's two things you need to do there. Make sure you add the height to the radius and then multiply by 1,000. And your answer should make sense. So always check your answer. It should be slightly less than the value of g at Earth's surface. 8.92 sounds about right. And really important, you overcome this very common misconception that as soon as you go into space, everything is weightless. That's just simply incorrect. It's clearly not true. So there's an inverse square relationship with distance and with the value of g. So slightly less than 9.81 would be about correct. And don't forget the units as well. After that, then we need to, for the speed, there's probably different ways we could do this. The simplest way is we know, well, we're assuming it's circular motion, so we can treat this as centripetal force or centripetal acceleration. So the value of g at that point, 8.92, or at that height, is the value of centripetal acceleration. So we've got this formula here. So we can rearrange it to make v the subject. We know the value of g. Once again, the radius. I think because it's r, it's the radius, it's very often just the radius, I think students would automatically go for 6,400. But remember that r represents the distance between the center of the planet and, in this case, the satellite. So we need to add the height onto the radius. Once again, whilst obviously these values vary a lot, but very often, especially in low Earth orbit, we're looking at very large velocities. So 6,000, 7,000, 8,000 meters per second, so kilometers per second. So expect to get a big value. If you got 50 or 100 or 350, then you should be thinking that's way too small. So expect a large value there. Question two looks quite simple. It's a very short question. We're only given this one bit of information in the question. Obviously, we're expected, or we will be provided with the mass of the Earth and the radius of the Earth. Calculate the time taken for one orbit. Now, there's several ways we could do this. So the way that I've approached this is by equating the centripetal force, mv squared over r, to Newton's law of gravitation. And we can see that little n cancels, and one of the r's cancel as well. And we can make v the subject. So this is a really useful formula. So this is the orbital velocity is equal to root big G big M over r. So you could, I would recommend you're confident with deriving this. You might be asked to derive it in a question. I think the exam board that I teach does not provide this in the formula booklet. Other specifications may do that, but I think you need to be confident with deriving this, or indeed remember it, because it's a really useful formula. So once we've got that, well, we're given the mass of planet Earth. As always, we need to add on the height in meters to the radius in meters, and again we get this really big value, 7,354 meters per second. Sounds about right, but that isn't the final answer because it wants the time. So here we assume circular motion, constant velocity, so v equals s over t, make t the subject, so s is going to be the circumference, so 2 pi r. Once again, it's the radius plus the height times by 1,000, multiplied by 2 pi, divided by our previous answer, and we get this value here. And you might be asked to write that in hours or minutes, perhaps. So that's the way I would recommend you do this. Other ways you could do it, probably similar to the previous question. You could calculate the value of g at that height, and then use this formula here, the version of centripetal acceleration, to work out the velocity. I think you can do this with Kepler's third law, which we haven't covered yet. So there are several ways you could get the right answer. Again, that can cause confusion because you need to make a choice, and you need to be confident with that choice when you're tackling this problem. So I would say the exam tip here is be confident with this derivation and remember it, but probably best to derive it. Question 3. So we've definitely upped the difficulty with this. So this would be quite a challenging exam question. It's a fairly typical type of question when we're looking at a point between two objects, in this case the Earth and the Moon, where the value of g is equal to 0. And we could explain this in different ways. We could think about the forces acting on, let's say it's a spacecraft. The attractive force of the Earth in one direction is balanced by the attractive force of the Moon in the other direction. And we should, the 0.9 is a fairly typical value, although we're not expected to know that. So how to answer this? There's different ways we could do it. The way I've chosen to do it is to say at this point, so 0.9 of r, then the values of g must be the same. Now, it might be easier for you to consider the values of forces acting in opposite direction will be the same, and then the overall force is equal to 0. You could do it that way, and then one of the m's is going to cancel on either side. But this way works as well. So we could write an expression for gravitational field strength for Earth. So that's big G, big M. In this case, that's the mass of the Earth divided by the radius of the Earth. So that's the distance, rather, from the center of the Earth to this point. And then we could write the other side of the formula. It's going to be big G. Again, this is the mass of the Moon. And RM, it's not the radius of the Moon. That's the distance from the center of the Moon to this point. That will be the values of G. And we can see that the big G is going to cancel. So the M's, well, the mass of the Earth we're given, so we know ME, we're fine with that one. We're trying to find MM, we don't know what that is. And at this stage, you might think, well, we don't know what these values are. They're different, but they are related. And if we know that the total distance between the centers is big R, then this value here is going to be 0.9. So we're a lot further from the Earth, and this will be 0.1. So it's 1 take away 0.9. We're a lot closer to the Moon. So that's quite a conceptual leap to realize that we can actually write an expression here for these two distances, both in terms of big R. So we don't need to know what the value of R is in this case. It's going to cancel. So then we can just make mm the subject. So big R cancels, or R squared cancels. We can make the mass of the Moon the subject. So it's going to be the mass of the Earth. And we've got 0.1 squared on the top divided by 0.9 squared on the bottom. So that squared is important. So 0.1 over 0.9 is not the same as 0.1 squared divided by 0.9 squared. And we can stick in the mass of the Earth, and we can work out a value for mass of the Moon. And as expected, it's going to be significantly smaller than the mass of the Earth. If it comes out as larger, then you've made a mistake here. Maybe you've got the 0.1 and the 0.9 the wrong way around. So you need to be confident with this type of algebraic approach. So especially if you're looking for the high grades, the A's and the A stars, it's not just going to be a case of get the formula and stick the numbers in. You might get the more simple questions like that. But if you're going to get the high marks and the high grades, then you've got to be really confident with this algebraic approach. There may be other ways of answering this question. This is the one that I've chosen, and I think this is the most algebraically elegant, perhaps. But even if you find another way of doing it, I would make sure you're confident with this approach, because this route allows you to get those higher grades.